Homework. Okay, so
electronically appropriate, push button, just seconds. That's all the rest. In the data section, I tried to make it where I can get them all on one page.
Okay, howdy. Good afternoon. It's time to continue with our lecture from Monday. So I guess I have all the papers, all the homework. And anyone remember what we did on Monday? We basically covered two distributions, were the uniform and the normal. Okay? So before we continue with the material, remember our second exam is on Wednesday. So on Monday, we're going to have our review. Typical review, basically I'm going to put the new homework today. We're going to discuss the homework on Monday. And if you have any other questions, come with your questions. We're going to answer those questions on Monday before the exam. So the exam is going to be very similar to the one you saw in terms of the format. It's going to be very similar. So you should expect a true or false part, first part, and also 4 to 5 questions depending on the length of the question. Okay? Any questions? So on Monday I'm going to list the topics. Should be, basically the material we cover after the first exam is going to be included in the second exam until the material we cover today. Okay, so up to today, the exam material will cover up to today's lecture. If you have your homework, please keep your homework until the end of the class. So Monday, we started discussing the normal. So today I decided to do something different, and basically I want you to see how this links to what you're going to be doing in your career as an engineer. So we're going to finish the normal distribution, and then I'm going to talk about a specific application in engineering where you're going to be using this type of probability distributions. Okay? So very quick, we started discussing the normal distribution. And for all these distributions, we are always looking at the shape. So look at this shape. This is like a bell. The importance of this shape basically dictates the distribution that you're going to be using to model a specific process. Okay? So that's why the shape of the distribution is very important. The shape, basically what you're trying to do is you're going to come up with a histogram or a graph, like a histogram, with your data. Your historical data, you're going to plot that data, you're going to come up with your histogram from that data, and you're going to try to fit one of the functions that we're discussing in this class to model the process you are interested in. So that's one of I'm going to discuss an application. You will see how that works after we cover the normal. Okay? Well, keep that in mind. So many phenomena can be modeled with the normal distribution, and the normal distribution is the most important continuous distribution that we're going to cover in class and in statistics. Okay? So the normal, we explain some of the applications. We talk about the density function of the normal. We stated in class that the density function is very difficult to integrate. So for that reason, we wanted to have a table that will help us to compute the probabilities from the normal. But if we take into account all the possibilities that we can have for different means and standard deviation, you will end up with multiple tables, a lot of tables, and the process will not be efficient. So that's why Okay, skip this. So this is basically properties. So that's why we come up to this part of the class, in which we talk about the transformation. So we are taking the normal distribution, the PDF, and we are transforming that distribution using this transformation for Z. Z is our new random variable from the normal. And the purpose of this is to come up with a single table that can model all the probabilities for the normal distribution. So what you do is you transform your X random variable using the mean and the standard deviation from your data to a new random variable Z. And using that random variable Z will have a mean, 0, and a variance equals to 1. And that's what we call the standard normal distribution. So we can get the data, we can fit the data, we can get the information from the normal. Let's say the mean equals 25, the standard deviation equals 100. We can transform that distribution to a 101 standard normal distribution using these Z values. So essentially what we are doing is taking the density function and transforming it to a density function in terms of Z. And again, this looks complex, but the idea is just to have one table to get the cumulative probabilities from the normal. Okay? So this is what we are doing. We are taking the normal distribution and we are transforming that normal distribution to a new normal distribution based on the standard normal distribution. So now that we have that transformation, we only need one table to find the probabilities from the normal. Independently of the mean and the standard deviation, you can always transform your normal distribution and use this table. Okay, which is very good because again, this normal distribution is used a lot. I passed this table last time, Monday. If some of you still don't have the table, it is available on Appendix 3 of your textbook, and I have some copies here. So if you don't have the table, you can ask me for a copy at the end of the class. So we started this using basically I used these examples to explain you how to use a table. So we covered this first example. We cover all these examples, just giving you practice on how to use the table from the normal and how the table, because again the table, let me go back to the table. The table is giving you the cumulative probability to the right of the random variable. Okay, so keep that in mind. So if I ask you for probability C less than, that's the information that the table is giving you. This area. If I ask you for a probability that is greater than, then you need to look at the complement. 1 minus the probability that I'm asking. And that's why we covered these examples. For example, this first one is asking for a probability greater than 1.26. So it is asking for this area. So we don't have that area from the table. We have the area to the left. So in that case, you need to look at the complement 1 minus this area to get this probability. Is that clear? Okay. So we cover this. And I think we also talk about this example. Again, here we have a random variable x having a normal distribution with this mean, this standard deviation, and I ask you to find the probability that x assumes a value between 45 and 62. Since we want to use the standard normal distribution from the table in order to get the probabilities, we transform the values of x, 45 and 62 using the transformation. So we get that z equals negative 0.5, 1.2. So now this probability for X becomes this probability in terms of V. We solve, we find these numbers from the table, and the probability of that happening being between 45 and 62 is 0.57. Okay, so that's where we're stuck. The next thing we're going to do is also related to normal curve, but we're going to use the table in a reverse way. So essentially, sometimes we are required to find the value of V corresponding to a probability that falls between the values listed in the table or the appendix. Okay, so we want to go from having a probability and having a probability, and we want to find the value of X that corresponds to that probability. So that's very easy. What you do is you take the transformation, now you already know, and you solve for X. So if you have the value for V, and you solve for X, you also have the value for the mean and the standard deviation, you can find the value of X. Okay, so it's basically doing the same thing, but changing the unknown. So let's look at this example. This problem is saying, given a normal distribution with mu 40 and sigma 6, find the value of X that has 45% of the area to the left. Okay, so you have the normal, the standard normal curve, and we want to know what is the value of X that covers 45% of the curve. That's the question. So what we need is for A, we require a C value that leaves an area of 0.45 to the left. So if you have your table with you, what you need to find is P of Z being less than equals 0.45. So what will be the value of Z that equals 0.45 from the table? So again, we refer to here. You're going to look at the second table. Correct. So this becomes the probability of Z be less than negative 0.13, and that will be equal to 0.45. But we still don't have the value of X. Remember, X is your horizontal basis. We have the value of Z.
I think it should be 0.103.
Negative.
0.103.
Let me double check.
So it's sorry, you're right.
Okay. So now we can find X. So X from here X will be equal to sigma times the value of Z plus mu. So X will be equal to sigma, let's go back, write the right formula, sigma times Z plus mu, and that equals 6 times negative 0.13 plus 40, and that equals 39.22. So the value of x, this x equals 39.22. Okay, so part B is saying it's asking for 14% of the area to the right. So as you know, this is a symmetrical curve. So finding this area is the same as finding this area. So this is same as finding an area of .86 to the left. So this is the probability of z be less than 1.08, and that will be equal to 0.86. So if you find x, this is 6 times 1.08 plus 4. Okay, and this is just to give you a better understanding of how to use the table, essentially. Yes?
Where did you get the negative?
This one, you call this value from in the table. Okay? And then you solve for x. Okay. So now we are ready to look at some applications of the normal distribution. And I want you to pay attention because you're going to have a lab based on this problem. So please be ready to ask questions, and then you're going to have the opportunity to work with the partner and try to solve one of these problems. Okay? So let's start with the first one. A certain type of storage battery lasts on average 3 years with a standard deviation of 0.5 years. Assuming that the battery is normal distributed, find the probability that a given battery will last less than 2.3 years. So what is the probability that we need to find? Correct. So it's the probability of x being less than 2.3. Okay? And x is the battery lifetime. That's our random variable. Okay? So we have the value of mu. We have the value of sigma, the standard deviation. So we can use the transformation z equals x minus mu divided by sigma, which is the standard deviation. And this problem is already telling you that this is normally distributed. So that's why you know that you're going to use the normal. Okay? So if you solve this, this is 2.3 minus 3 divided by the standard deviation. And this is 2.3. Then you get that the value of z is minus 1.4. So the probability of x being less than 2.3 equals the probability of the transformation for Z less than minus 1.4. So anyone can tell me what is the probability? So it's minus 1.4. So look at the table again. Correct. So you have to find the negative table. Okay, so minus 1.4 is 0.0808. Questions? I have extra tables here. If you don't have the table, so as I mentioned on Monday, a big part of your exam is going to be from the normal. So it's very important for you to understand what we are doing. Okay, so this one was very easy. Let's look at the next problem. Any questions about this problem? You can check the table again and find that values, negative 1.4, and check if you get the same value for the probability. Okay, the next problem is a little bit more complicated, and you will see why. So in this one we have an industrial process, and the diameter of a ball bearing is an important measurement. The buyer sets specification for the diameter to be 3 plus minus 0.01 centimeters. The implication is that no part falling outside these specifications will be accepted. So if you have a part that is greater than, or the diameter is greater than 3.01, you will not accept that part. So it is known that in the process, the diameter of the ball bearing has a normal distribution. So you can represent the diameter for all the parts based on your historical data using a normal distribution with a mu or a mean of 3 and a standard deviation of 0.005. Okay, so the question is, on average, how many manufactured ball bearings will be scrapped? Okay, so you want to predict based on your process and based on your mean and standard deviation, how many of those ball bearings that you're producing are going to be defective. Okay, so let's try to look at this. So the specification limits, again, specification limits. What are those? What are the limits for this tolerance, for this ball bearing? Correct. So let's call X1 2.99 and X2 equals 3.01. So if you look at this graph, the curve, we can say that this is 2.99 and this is 3.01. So the parts that falls in this area and the parts that fall in this area will be scrapped. Okay, because those are the ones that are less than this number and higher than this number. If the diameter is within this number, it's good. Okay, so what we're trying to estimate is how many will fall on those or above or below those limits. So we have the values of X. We know that the process is normal, so we can use the transformation of the normal to solve the problem. So the corresponding Z values are Z1 equals 2.99 minus the mean, which is 3, divided by the standard deviation, and that is equal to minus 2. See what we're trying to do? We are taking those limits and we are transforming those limits to values of Z, because we want to use the standard normal to get the values from the probability table. Z2 equals 3.01 minus 3 divided by 0.005. So this equals 2. Okay, so now the problem is, again, the question is how many manufactured ball bearings will be scrapped? So what is the probability that you're trying to find? You want to find this area and this area, right? So with the sum of this probability and this probability. Yes, sir.
Since it's symmetric, you just calculate one and then just double it?
Yes. You can multiply times 2. Yes. Correct. But in this case, we're going to take them separately. So you have the probability of Z being less than -2 plus the probability of Z greater than 2.0. And if you find, since it is symmetric, if you find this probability, you'll see from the table that it's the same for this one. So this is 0.0228 and this is 0.0228. So this equals 0.0456. And again, to find this probability, you need to look at the complement. Okay? 1 minus the probability of Z being less than 2.0. Questions? Okay, so again, it's very important for you to understand how to use the table first, because the table is giving you the probability to the left. So for these cases, maybe it will be helpful for, so this part here is 1 minus the probability of Z being less than 2.0. So that's how you find the probability from the table for this part. Okay? And when you find this, you will see that it's going to be equal to this, 0.028, which is the same as this because it's symmetric. So so we know that -2 is going to be, if you look at the table, is going to be 0.0228, right? That's no question with that. If you look at 2.0 positive, it's going to be 0.96, 97, 72. But if we subtract this from 1, you will get it. Okay? Let's move to the next one, and the next one is going to be more interesting for those in electrical engineering. So what we have here is a normally distributed current. So suppose the current measurement in a strip of wire are assumed to follow a normal distribution with mean of 10 milliamperes and a variance of 4. What is the probability that the measurement will exceed 30? So how do you state that probability? It is the probability of x greater, less than, greater than, correct? You want to know what is the probability of exceeding that current. So again, we know that this is normally distributed. So we can use the transformation. So it's the probability of 13 minus 10 divided by the standard deviation. Why is the standard deviation 2? Because the problem is giving you the variance. Okay? So the standard deviation is the square root of the variance. And this has to be greater than 13. This is z. So this is equal to the probability of z being greater than 1.5, which is equal to 1 minus the probability of z be less than or equal to 1.5, because we need to look at the complement. So if you find 1.5 here, it is 0.9332. So this will be equal to 1 minus 0.9332. And that probability is very low. It's 0.067. So the probability of finding a current about 13 millimeters for this wire is very low. It's 6%. Okay? So if you need to plan for a circuit and you need to know what would be the probability of exceeding a current for your model, this is the type of analysis you will have to do. So if you know that this probability is 6% for your design, if that is high, you will have to revise your design. If it is not high based on your design, then you can continue and focus on other parts of your design. Okay? So what is the next question is saying, what is the probability that a current measurement is between 9 and 11? So it's basically the same. You have this probability of x being within x 9 and 11. So if you do the same transformation for the normal, you will get the probability of being within 0.5 and 0.5. So how would you solve this? Oh yeah, that's the z. I'm sorry.
On the probability of 0.5.
Correct. Everybody see that? We are looking at this. So we are looking at this area, minus 0.5 and 0.5. Okay? So if you get the probability for 0.5, that probability is going to take all this area. So in order to find only this area, you need to take this probability and subtract this one. Is that clear? So what you do is, the probability of z being less than 0.5 minus the probability of, excuse me, z, this is z, less than minus 0.5.
Find the values for z again, like 0.5, negative 0.5, 0.5.
Yes, negative 0.5. If you look at your table,
Right.
you'll see that this first column has the value of z, right? And on top, you'll see that the top row will have additional values still for the Z. So if you look for negative 0.5, you need to look at the table for the negative value. So you will go to minus 0.5 in this column, first column, and you know that it's just minus 0.5. So it's the first column, second column from the table, 0.38, 0.3085.
Right.
Got it?
No. How are you getting from 9?
Oh, from 9 to 11?
Right, and then get 0.5.
Yeah, I skipped one step, but basically it's using the transformation. Yeah, I basically skipped this step.
Gotcha. All right.
Okay, but that's a good question. So from here to here, you need to use the transformation. Okay? So you have 9 minus 10 divided by 2, and that's negative 0.5. And then you have 11 minus 10 divided by 2, and that's 0.5. Okay? Any other questions? Okay. So now we have the values for Z, so we can look at the values from table and get the probability. So in this case will be 0.069, 146 minus 0.3854, and that's equal to 0.3829. So the probability of having a current within 9 and 11 is almost 40%. Okay? So if that's good for your circuit, then you're doing fine. If it is not, then you're going to have to revise your components or your specification. Okay? Questions? Okay, so the last part is determine the value for which the probability that the current measurement is below this value is 98%. Okay, so now we have the probability, and we want to find the value of X that will give you that probability. Okay, so X again is the current, so we want to find that current that would basically cover 98% of the current that you can have in your circuit. So for that, again, we have part C. So we are finding C less than Z, that is equal to 0.98. So from the table, you need to find out what is the value of Z that will give you 98% or close to 98%. 2.06, 2.05.
0.05 is like
Yes. So whichever is close, I'm going to use 2.05. So this is going to be equal to the probability of Z be less than 2.05. And what do you do next? You need to find X.
X equals sigma Z plus B.
Correct. So this is what we discussed at the beginning of the class. So X equals 2 times 2.05 plus 10. So that current will be equal to 14.1 milliamperes. It's 14.1. Okay, so you see how this is connecting with your field. Okay, so if you're an electrical engineer, I can tell you, you'll be using this type of analysis. If you're designing circuits, you'll be using this. Okay. So now I have the next exercise for you to work with the partner. So I'm going to pass this. You can work on group of 2 or 3. And this is basically, again, applying the normal distribution. If you don't have the table, I have copies. Okay, so you have 10 minutes. Five minutes. And this is the type of problem you should expect in the exam. Okay, so if you're able to solve this type of problem, not the exact problem.
If you have if they're equal, like distance from average to
If you find the right one,
that's our one line. Is the same sheet back there?
it's going around. I just passed it.
Oh.
Ten minutes. For this problem, part C, just make sure you're using the right number for the table. It exceeds 0.95, but it's greater than. Okay, so you need to look at the complement.
Yeah. So. Yeah. I think he's right. You got 5
Okay, 1 minute. Seconds. Any second? Ten seconds. Okay, so you can start passing the solution.
Yeah.
Fingers. Okay, I got all of them. Any other papers? Okay, so for this lab, so these are 5 points. You got, all of you got the 5 points. I just want you to practice. The exam is next week. I'm not gonna penalize you. So 5 points if you submitted your lab, but we're gonna discuss the problem, okay? So, first part is the probability of x being greater than, less than, equal to. What is this statement?
Equal to, is less than 60.
Less than 60 to 50, correct? So if you do the transformation for the normal, you get z less than 6,250 minus 6,000 divided by the standard deviation, which is 100. So this is equal to the probability of z being less than 2.5. So this is 0.9937. Questions? So that one was easy. Second part, this is a little bit more complicated, but it's similar to what we did in the previous problem. So x within this. So if you get the values of z, what would be those values? Z
between -2 and
Oh, oops, sorry, yeah. Looking at the wrong problem. So it should be between 5,800 and 59, which if you look at these, this is going to be -2 and -1. And if you solve this, this is the probability of z being less than -1 minus the probability of z being less than -2. And this equals 0.13591. Questions? Okay, the last one. last part is the, I think, tricky one. It is asking for the probability of x being greater than x equals 0.95. So look at this, exceeded. So we have the probability of x being greater than the value equals 0.95. So if you were to solve this, you have to look at the complement. So this is 1 minus the probability of x being less than x equals 0.95. And this becomes the probability of x being less than x equals 0.05. Is that clear? You're looking at exceeding 95% of the sample. So you need to state that probability correctly. And that would basically guide you to solve the problem.
Is that probability on term B, is that 0.1359? Is that like competitive, like it happens a lot, that probability, that number?
This is coming from the table.
Yeah, okay, that's
yeah. Any other questions? Okay, so now if you solve for x, you'll get x minus 6,000 divided by 100. What would be the value of z? Negative 1.65. So x will be equal to 58.35. So that would be the strength that you have to apply to exceed 95% of the sample. Okay, so this covers the normal. Again, big part of your exam will be based on the normal. But now we're going to transition to another important distribution, which is the exponential. And you're going to hear a lot about the exponential in your career as well. So, can I move to the next set of slides? Okay. But before we get to that, so now we're going to move to gamma and the exponential. But again, to show you